beneficial or problematic, the pros and cons of facial recognition technology, and ethical concerns of AI and how we can use it in an ethical manner. So a brief introduction into data and ethics. Ethics are the moral principles that govern a person's behavior or the conduct of an activity. It is concerned with how an action is seen in society and your own values and feelings, which is a very human phenomenon. Sorry, someone's speaking in the background. Could you mute it? Thank you. So when ethics is coded for artificial intelligence, they are basing everything off of data fed into it. So machines lack the ability to know for themselves if something is morally right or wrong. Therefore, it is up to us to manage how ethical the data inputs and outputs are. Today, we'll be explaining the connection between data and ethics in AI. As you can see below, the ideal scenario is the nearly everything that is legal or doable using AI. It overlaps with being ethical. However, in the real world, there are situations where ethics and legality do not align. The area it doesn't overlap is the more problematic side of AI use. Some new AI technologies have made information collection quicker, more accurate, and more accessible. However, then arises some ethical concerns over how the data is collected, used, and stored. Before we get into focus the benefits of artificial intelligence, what is it? So artificial intelligence is the ability of a computer to learn and think. Everything can be considered artificial intelligence if it involves a program doing something that we would normally think would rely on the intelligence of a human being. The artificial intelligence is used in multiple ways, and in today's world, the development of AI has aided in revolutionizing industries, making technological strides, and improving security. So what are the main benefits of artificial intelligence? Firstly, it allows for reduction of human error. AI software and programs make decisions based on previously gathered information and apply a certain set of algorithms. This ensures that the errors are reduced and the precision of accuracy is increased. An example of this is the use of AI in the production processes. Japanese companies like Bridgestone use AI systems to monitor the quality of their tires during production processes, detecting and eliminating human errors in the initial stages. Secondly, there is no time limit to its usage. What that means is that AI systems are used to monitor performances even during non-working hours. A real-life example of this is the use of AI in educational institute and helpline call centers. So calls received by these institutions involve multiple queries and issues which can be handled effectively and sorted by AI. Thirdly, it increases convenience. So AI is used to modify and simplify multiple tasks on a day-to-day basis. An example for this is the Amazon automated shopping experience. Amazon Go stores are fully powered with fusion sensors and cameras that detect what you pick. By the time you finish collecting your items, your purchase is made without any intervention. And lastly, is it provides increased security in many cases. So AI, machine learning, and threat intelligence can recognize patterns in data to enable security systems to learn from past experiences. An example of this is people tracking. So video processing is done in real time to analyze and identify suspicious events that can pose a threat to an enterprise. Video analytics technology effectively allows surveillance softwares to reason and detect irregular behavior and identify dangerous activities that might be ignored by a person. So how is it problematic? As you already know, many people are wary of AI as it raises ethical concerns about privacy, jobs, security, and intent. So we will go into detail about all the forms of ethical dilemmas later. For now, let's move on to some MDN theoretical content.
Thanks, Raksha. Can everyone hear me okay?
Yes.
Cool. So, hey everyone, I'm Aiden. I'm part of the deep learning training team. And today, alongside Jason and Johnny, we'll be speaking about the applications of deep learning. So mainly in reinforcement learning and natural language processing. Before we get started, let's quickly recap on our series content so far. So firstly, what is deep learning? So deep learning is actually a subset of machine learning, which in turn is a subset of artificial intelligence. So artificial intelligence as an academic discipline was founded in 1956. The broad definition of artificial intelligence covers any device that in some way can mimic cognitive function. So machine learning, however, came around in the 1980s and are used to identify any algorithm that can take in data, learn from that data, and then apply what they have learned to make better decisions. Deep learning is once again a subset of a greater field, this being machine learning, and is used to describe an algorithm that contains large artificial neural networks. The models are designed to continually analyze inputted data with a logical structure similar to how a human would draw conclusions. So the term deep often refers to the layers involved within the neural net. Now, in terms of reinforcement learning, in this series, we have mainly been just exploring one type of machine learning, supervised learning. And this is defined by its use of labeled data sets to train algorithms to classify data or predict outcomes accurately. These are generally applied to data sets that are labeled, meaning for every image, there is a label, such as, I guess, when you did a worksheet in school and there was always an answer sheet for every question. So another way of thinking about it would be, it's very similar to when a teacher is supervising a student on whether they're doing a task correctly or not. So unsupervised learning, on the other hand, is something we haven't really touched on that much, and it's used for discovering patterns and clustering unlabeled data sets. So unsupervised learning is, as it sounds, unsupervised with no labels, as opposed to supervised learning and no feedback. So the purpose of unsupervised learning is to generally find unknown or hidden patterns within the data. Lastly, the focus of today's workshop, however, is our last type, reinforcement learning, or RL. RL is a study of how intelligent agents ought to take actions in an environment in order to maximize the notion of cumulative reward. So through many, many training steps, the algorithm attempts to maximize reward, and in doing so, learns optimal strategies. So what are the key ingredients of, I guess, deep learning as a whole? Deep learning, we have 4 ingredients that we'll go over today to build a successful model. These include a varied data set that has a large amount of data for the model to learn from. Data is by far the most important factor. As for deep learning, we need data and lots of it. The larger the data set, the better. A model with an architecture suited to solving the required problem. So we can either use a pre-trained model using transfer learning, create a network from architecture from scratch. Number 3, we need a well-planned training cycle. And number 4, a good evaluation of the model to kind of determine if further investigation is required. So with that, let's get started on reinforcement learning. So I have got a quick video. I've got a quick video to kind of demonstrate reinforcement learning. It's made by OpenAI. So I think if we could quickly play that video, that would be kind of a really good introduction.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide-and-seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment, truly complex and intelligent agents will one day emerge. On Earth, the simple
Okay, cool. Sweet. So yeah, that's a video by OpenAI. I found that really engaging as an introduction to, I guess, what RL is and the power of RL. So yeah, I hope everyone really liked that, I guess. So now let's just have a chat about, I guess, the applications of RL. So RL is so well known these days because it's the mainstream algorithm used to solve different games and sometimes achieve superhuman performance. So the most famous one must be AlphaGo and AlphaGo Zero. So AlphaGo trained with countless human games, already achieving superhuman performance in Go, Shogi, chess, and Atari games. So similarly, OpenAI has been able to achieve expert level performance on the popular game Dota 2, also just using reinforcement learning and self-play. So in industry, learning-based models are used to perform various tasks. So apart from the fact that these robots are more efficient than human beings, they can also perform tasks that would be very dangerous for people. A great example is the use of AI agents by DeepMind to cool Google data centers. This led to a 40% reduction in energy spending. The centers are now fully controlled with the AI system without the need for human intervention at all. In the finance world, RL agents can decide trading tasks, such as whether to hold, buy, or sell. The RL model is evaluated using market benchmark standards in order to ensure that it is performing optimally. So the automation brings consistency to the process. And unlike previous methods where analysts would have to make every single decision, IBM, for example, has a sophisticated reinforcement learning-based platform that has the ability to make financial trades. So it computes a reward function based on the loss or profit of every financial transaction. So what's the big idea of RL? So RL is the training of machine learning models to make a sequence of decisions. So the agent learns to achieve a goal in an uncertain and potentially complex environment. The computer employs trial and error to come up with a solution to the problem. So reinforcement learning operates on the basis of a mathematical framework called Markov Decision Process, or MDP. Formally, we have a set of states, or the state space, a set of action, or the action space, so a set of actions, or the action space, and a set of rewards. So usually these sets have a finite number of elements, and the goal is to maximize the total reward. So let's delve deeper into these key terms. So in each time step, so t equals 0, t equals 1, t equals 2, the agent receives some representation of the environment's current state. So this also includes the configuration of the agent at that particular point in time. So for the example of Pong, in front of you, the state would cover the position of the ball as well as the position of the paddles at any one point in time. Now, the agent observes the state and selects an action. So it may select an action within the action space, which in this case of Pong is just either you move the paddle up or down. So along with the state, this gives us a state action pair. Now, to discuss a bit further about rewards, so for each state action pair that we're talking about, the agent receives a reward and time is then incremented to the next step. So the process of receiving a reward is based on an arbitrary function f that maps state action pairs to rewards. So this is called a reward function, and in many cases, it may be a function that the developer needs to actually define before training even begins. Return is a cumulative reward over a game episode, which could potentially be, in this case, each round of this Pong game. And we can see that cumulative reward is measured over time as the score, so 2 to 18 or 2 to 17. Now, to understand value, we need to talk a little bit about policy. So a policy is a function that maps a given state to probabilities of selecting each possible action from that state. So when speaking about policies, formally, we say that the agent follows a policy. So for example, if an agent follows policy pi, so pi just denotes policy, at a specific time t, then pi of a given s, so a being an action and s being the state, is actually the probability that an action is taken at a specific state. So this means that at a specific time under a specific policy called pi, the probability of taking an action an action A in state S is pi of A given S. So this is important when it comes to value or value functions. So value functions are functions of states or of state action pairs that estimate how good it is for an agent to be in a given state or how good it is for an agent to perform a given action in a given state. So the state value function for policy pi tells us how good any given state is for an agent. So in other words, it gives us the value of a state under a given policy. Similarly, the action value function for a policy tells us how good it is for an agent to take a given action from a given state while following that policy. So in other words, it gives us the value of an action under a specific policy. So formally, the value of an action for a given state under a specific policy is the expected return from starting from state S at time t, taking action A, and following that policy pi thereafter. So that brings us into Q-learning. And conventionally, the action value function that we were talking about is referred to as the Q function. So the output from the function for any given state action pair is called a Q value. The letter Q is used to represent the quality of taking a given action in a given state. Q-learning is the first technique that we'll really go into, and that can solve for the optimal policy in a Markov decision process. So the objective of Q-learning is to find a policy that is optimal in the sense that the expected value of total reward over all successive steps is the maximum achievable. So in other words, the goal of Q-learning is to find the optimal policy by learning the optimal Q values for each state action pair. Now we can store all these Q values in a table called the Q table, where you can see in the top right. However, while this method can play many games with generally a low number of states, such as noughts and crosses, for example, it doesn't really scale well to games with millions of possible states, such as chess. So then come our other algorithms that we've actually used in MDN projects. So some of these algorithms that we've used are firstly deep Q networks, or DQNs, which is pretty much a continuation of Q-learning discussed before. But in this method, we make use of a deep neural network to estimate the Q values for each state action pair in a given environment. And in turn, the network will approximate the optimal Q function in the in the Pong example, this kind of requires us to consider every possible location of the paddles and ball. Another algorithm we have used is called actor critic. So in this approach, we use a distribution to select actions from a continuous action space. And we've used this approach in AWS DeepRacer. Actor critic learning is a reinforcement learning technique in which you simultaneously learn a policy function and a value function. So the policy function plays the role of the actor. It picks what moves to play. The value function is the critic. It tracks whether the agent is ahead or behind in the course of the game. So it's kind of like two neural networks improving each other. So that feedback guides the training process, and in the same way that a game can kind of that a game review can guide your own study. So now for our first breakout room discussion session, I guess just a bit of a preface. This was intended as a very soft introduction to reinforcement learning concepts, and it's a lot of new content, so we don't expect you to kind of memorize or understand it all. But we've come up with some discussion questions that you can discuss with some of the demonstrators here in breakout rooms. And there is a practical provided at the end of the workshop, which provides a bit of a demo of RL showing how it can be used. So yeah, so I guess we're ready to move into breakout rooms. So I hope that breakout room session kind of helped understand all this content. We will have a practical at the end, so feel free to reach out to any of the demonstrators and ask more about this stuff. For now, I will pass it back to Raksha, who will be talking about a bit about facial recognition.
Thank you, Aiden. So in order to discuss the problems of AI applications, let's focus on a specific example that is commonly used in our day-to-day lives, which is facial recognition technology. So facial recognition technology is a biometric technology that distinguishes facial features to identify a person. It works in three main ways. The first one being the face detection process, which is an essential step in detecting and locating human faces. The second step is the face capture process, which transforms analog information, such as your face, into a set of digital information, which can either be data or vectors based on a person's facial features. And the last step is the face match process, which uses data provided to verify if the detected face match the ones in the database. So let's focus on the pros of or the real life applications of the facial recognition technology. So as discussed before, facial recognition technology can be used to increase safety and security in multiple ways. On a day-to-day basis, it is used to unlock phones and provide seamless verification experiences in airports and workplaces. Law enforcement agencies use this technology to uncover criminals or to find missing people using matches that are available on the security database. It also is used to protect businesses against theft. So business owners use facial recognition software and security cameras to identify known or suspected thieves as they enter their stores. This is like a preemptive security measure, which can help prevent shoplifting. Another way is that it increases your convenience when you check out from queues conveniently, or even tag your photos or friends on social media. Recently, it has also been used to improve medical treatments. Facial recognition softwares have been utilized in hospitals and hospital settings in order to detect genetic disorders in healthcare. So an example of this is the use of an app called Face2Gene. A link is provided in the slides. When you get the slides later, you can go check out the website to learn more about it. So despite the ample advantages that we get from using this technology, there are a few downsides. The first one being it's a threat to an individual's privacy. So people don't like having their faces recorded and stored in a database for unknown use in the future. Due to this, multiple cities like San Francisco, California, and Cambridge have banned the storage of images in databases. In order to tackle this, law enforcement make use of real-time facial recognition surveillance. Second reason is that it is not effective in identifying women and colored people. So as discussed in our previous workshop on biases, facial recognition softwares have been ineffective in detecting people of color and women. So in 2018, a gender shade study was conducted on the facial recognition softwares used by companies like Amazon, IBM, and Microsoft. In the study, it was found that the algorithm performed worse when detecting women of darker skin tones, with an error rate of up to 34% higher when compared to data of males with lighter skin. Thirdly, it provides an opportunity for fraud and other crimes, as it's unable to detect the difference between prosthetic masks and people's faces. In 2010, CNN reported that an Asian man in his 20s pass through a Hong Kong passport control system undetected. And despite wearing a mask that distinguished him as an elderly white man, which resembled the individual in his stolen passport, he wasn't found. So these cases are increasing till date. And there hasn't been a way facial recognition softwares have been able to tackle this. Fourthly, it provides an opportunity for data vulnerabilities. So there is also a concern about the storage of facial recognition data, as these databases have the potential to be breached, and in the wrong hands, it can be very dangerous. So tying into the disadvantages of facial recognition technology, let's look at the broad picture of the ethical concerns of AI in general. So before we reveal them, let's move into breakout rooms to discuss the ethical concerns of AI and their implications. So you can discuss the common ethical concerns of working with AI, and if you could think of any examples, that would be great. And also discuss in your rooms, what are some considerations individuals and industries have to make to take into account when they have to work with AI, and who do you think is responsible for handling AI ethics? You've had a chance to discuss in breakout rooms. Does anyone want to share their answer of what they've discussed or any interesting points in their during their breakout room session? Feel free to unmute yourselves or just put it in the chat.
Someone from my breakout room, Raymond, I don't know if you want to talk about this, or I can talk about how you introduced the idea of people having different ethics, like everyone perceives ethics differently. So how, as a collective making an artificial intelligence technology, how do you decide on one final ethic to implement when people have such different ideas about ethics?
Yeah, so yeah, pretty much I guess you summarized what I said. But yeah, it's like, I guess another thing is like ethics like changes over time. So it's like, do we like allow the AI to like adapt to it, or yeah, like how do we make these decisions on like yeah, there's like I think Connor in my breakout room sort of mentioned like, well, like something similar to like the trolley problem. It's like, do we choose to like kill one person or like 5 people? And yeah.
That's a good point you mentioned, Sophia and Raymond. We'll discuss about this after some of the MDN content. Does anyone else want to share any further things that they've talked about?
Right, so in my breakout room, we've talked about how ethics can actually be defined by culture. So in certain countries, usually Asian countries, specifically like China or Singapore, if they don't really mind if they were to share their own individual data, as long as it's like helping the society. But for other societies, specifically those in Europe, so taking, for example, Germany or France, they take individual privacy really seriously. So, and yeah, we just thought that it's culturally dependent.
That's a great point. Anyone else has any other points that they talked about?
In my breakout room, we kind of had I think a good discussion about the interpretability of like the AI systems. So we were talking about how there's a lot of research now coming into trying to make the black box of the AI systems more interpretable. So it'll be easier for like the end users and everyone else to understand how did the AI learn about this, like learn to do this decision making or stuff like that. Which I think that will be a really good thing to help with, I guess, judging a bit of the ethics behind the AI, and also helping to try and spot kind of biases if there are any.
That's a really good point, Daryl. I think, okay, all of you have raised wonderful points that we can discuss further. Before I get into the answers or to further discuss the answer to this question, let's move back to some NGN content. And then at the end of the session, we'll come back to ethics in AI.
All right. Hi, everyone. My name is Johnny, and I'll be going through NLP, or natural language processing, today. NLP enables computers to understand natural languages as humans do. Today, we'll be learning what types of deep learning models are suitable for NLP tasks, as well as how the model functions. Like RL, we'll start off with an introductory video.
What is natural language processing? Imagine you're at the hairdresser. The receptionist tells you the stylist is free. But what does that mean? That the haircut doesn't cost anything? That the stylist has been released from prison? Of course not. It means the stylist is ready for your haircut. You know that because you have context. Computers are programmed to identify written and spoken words, but to really communicate with people, they need to understand context. That's where natural language processing, or NLP, comes in. Computers use NLP to look beyond individual words or phrases and understand the context they're being delivered in, often enough to communicate with virtually anyone in real time. Natural language processing lets virtual assistants like Siri and Alexa understand that when you ask them to play some rock, you're not asking Siri to pick up a guitar or start banging stones together, but to play some tunes. We hope this video on natural language processing makes sense.
Okay. All right. So the key takeaway from that video is that we have to derive context from written text in some way, shape, or form. The problem is that machines can't simply process text in raw form. They need us to break it down into some sort of numerical format, some vector representation, as you may. So this is where where concepts such as bag of words and TF-IDF come into play. Both of these are techniques that help us convert text sentences into numeric vectors. Both incorporate some sort of frequency of terms. These methods are explained later in the practical as well. There's also a method called word embedding, which consists of word vectors. Particularly, how it works is that you have words which are similar in meaning, contain vectors that lie close to each other in space, measured by Euclidean distance, and words that are unrelated lie far apart. In any case, the first step is to vectorize text in some manner for NLP tasks. Before text is provided as input to our models in numerical form, there are some basic pre-processing steps that are generally used within NLP tasks that should be addressed. Most basic and often first method applied to strings is to tokenize, where each word within a sentence is broken up into their constituents. So for example, we have New York is the most densely populated city in the United States. We've broken up into each of their singular words. And after these sentences are broken up, sometimes words undergo stemming or lemmatization, whereby these methods revert words to their root and base form. As shown on the diagram on the right, both stemming and lemmatization changes keywords to the root form. However, stemming relies on some naive rules that will remove contextual information. And as a result, lemmatization is often used over stemming. And finally, we have the removal of stop words, which are occasionally utilized, as they remove words such as the, is, and, such that meaningful tokens are kept for inputs only. This will simplify a model. However, the obvious drawback is that contextual information is also lost in the process. Now, we can recall back to the last lecture, we went through a supervised learning track of image classification. Many NLP tasks also undergo supervised learning for tasks such as text classification or sentiment analysis. Usually within the data within supervised learning rather has an associated label. For example, imagine there's a tech sentiment analysis problem where we scrape movie reviews from IMDb. It would classify whether the review was good or bad. There exists an obvious mapping between input and output. If you want to tackle something like sentence prediction, however, the training data doesn't come with inputs and outputs, rather it's just a sequence of inputs for sentence prediction. In other words, we want to train a model on just the text alone without labels. But in that case, how does it select its output? We'll answer that very soon. But now let's step into sequence modeling. Let's step into sentence prediction even further. Say we have a model that just generally understands English, and we can tackle another set of NLP problems called sequence modeling. We are mapping the probability of a sequence rather than mapping between inputs and outputs. We want a machine learning model to generate likely sequences, or in our case, likely sentences. Specifically, we require a neural network to estimate the probability of a sequence. All right, now say we have the sentence, I went to the kitchen this morning to make. Can you guys provide a possible output for the sentence? Just type in the chat for me what could be outputted in this right here. Breakfast, cup of coffee, breakfast, sandwich. Yeah, no, these are all very valid points. We arrive at the point where multiple answers can finish the sentence. As mentioned before, because we're mapping probability sequences, if we have an output such as, I chose bacon, it would mean that bacon was the most likely word to be chosen based on the data it was trained on. However, let's say we're asked to predict the next two words of the sequence. How would we do this? Well, we would use the previous output and change it to an input for our neural network. In our case, we predicted the word bacon, and that will be converted into the next input. And the model will have to predict the next output with the sequence. I went to the kitchen this morning to make bacon. And then it could predict output, such as and. And if we keep on doing this, where we have the model of the third word, the output and is converted to the input, and the model predicts the next word with the sequence. I went to the kitchen this morning to make bacon and, well, bacon and eggs, right? This intuition of outputs becoming inputs are essential in understanding a type of neural network called recurrent neural networks, where there exists loops within the hidden layer itself. Recurrent neural networks. All right, now let's take a step back as to explain why we think introduce a new type of neural network architecture in the first place. In the past lectures, we introduced you guys to regular feed-forward neural networks, the diagram on the right. In these feed-forward neural networks, the information only moves in one direction, from the input layer through the hidden layer to the output layer. The information moves straight through the network and never touches a node twice. You may ask why we can't use these neural network architectures to model sequences too. Well, you can, but there are some key problems that arise. Let's first address verbal length input. In these feed-forward neural networks, the input layer must always remain a fixed size. In the diagram, it's 4, but an obvious problem arises if we need to input sentences of variable length. And obviously, you can have sentences of length, I don't know, 3 to like 20, for example. Another problem that arises is that we don't have parameter sharing. The idea of parameter sharing makes it such that a network that does not have to relearn previously learned sentences. Let's take the two sentences, I ate an apple yesterday, and also yesterday I ate an apple. Both of these have identical meanings, but the phrase I ate an apple appears at different timestamps. By sharing parameters, you only have to learn what that part means once. So I ate an apple, you only need to learn what that phrase means once. Otherwise, you have to learn it for every single timestamp that it occurs within the model. So within the regular feed-forward neural networks, these semantics learned about the sequence won't transfer if they appear at different points, or won't transfer if they appear at multiple points rather. This increases computation time and, well, isn't preferred. In addition, long-term dependencies are also lost within traditional feed-forward neural networks. If you think back to the previous example, where you want to predict the output of "I went to the kitchen this morning," most feed-forward neural networks have already forgotten "I went to the kitchen," and thus has false context. For that reason, we need to introduce something new called recurrent neural networks. To use previous contextual information to affect future outputs, we add loops in the neural network such that previous information is sent forward in time. This is the essence of a recurrent neural network, or as mentioned further on, as RNNs. An RNN contains a looping mechanism that acts as a highway to allow information to flow from one step to the next, often known as the hidden state. This hidden state, S, is a representation of previous inputs, or in our case, a representation of previous words. So the hidden state stores information and is repeatedly modified in information seen thus far as to retain context. All right, now let's take an application. Let's say we have an RNN and we want to build a chatbot that can respond with sequence prediction. If the user types in, the quick brown fox jumped, we'll first utilize some tokenization and memoization, some pre-processing methods before, where we break up individual words and simplify our inputs. For demonstration purposes, the other examples will have the original sentence, the quick brown fox jumped, to retain clarity. Okay, so the first step is that RNNs operate sequentially, so we have to feed inputs in one step at a time. The first step is to feed the into the RNN. The RNN encodes the and provides an output. In the next step, we feed the word quick to the hidden state from the previous step. Remember, the hidden state represents information on all previous steps, and on the node above quick, the RNN now retains information on the words the and quick. We repeat this process until we reach the input jumped. By this final step, the RNN has encoded information on all words, as indicated by the color distribution within the node above jumped. And using this hidden state, contextual information is retained and we get a final output. Over. The quick brown fox jumped over. All right, now let's go a bit further into the details. Remember, in the RNN, we will be given a probability distribution of possible outputs. Specifically, the output y is a vector with values between 0 and 1, and the sum of the elements add up to 1. Say the possible outputs in this case, for example, is over and across, and the model was like the word with the highest probability to be outputted. So in this case, because over has probability of 0.75, it would choose over rather than across for sentence prediction. If you want to continue this prediction, the RNN also uses the representation of the word over as an input. We'll get to denote this as x6, and also the previous hidden state S5 to calculate the new hidden state, and in turn calculate the new a new output for the next word afterwards. Specifically, we use two variables and we multiply them with two constant weight matrices, xx, wx, and wrec for w recursive to find the new hidden state. And let's see how we optimize this model. Within the RNN model, we still use backpropagation to optimize three parameter matrices specifically, denoted by wx, w recursive, and such that it can predict sequences more accurately. We also use the tanh, the hyperbolic tan function as a nonlinear activation function to model nonlinear dependencies that are inherent within sentences. In addition, if you look at the parameter w recursive in the diagram on the right, it remains the same in each timestamp and is repeatedly used to calculate the next hidden state. Now, if you think about it, if we don't have the activation function, tanh, that bounds between -1 and 1, we will just have a multiplication of many weighted values. So some value to the power of how many words you have. So we use tanh to bound these weights between -1 to 1 to stop. Okay, now, although this is all well and good, there are some issues with RNNs and how they work. Specifically, we encounter something called the vanishing gradient problem. In the previous example, than in the image you see right there. You may notice the odd color distribution representing the hidden state. Mainly that the colors are not equal in area if you look at the word jumped, where the blue is very tiny compared to where it was when it was represented by quick, back in state number 2. We use this to highlight the vanishing gradient problem and short-term memory. Within feed-forward neural networks, we stated that it doesn't take long-term dependencies well, and with RNNs, it also runs into this problem. As RNNs process more sequential data, it has trouble retaining information from previous steps due to the nature of backpropagation. And before we step into that, let's recall what backpropagation is. Okay. So first, it makes a forward pass. So let's examine how backpropagation works and how it's involved in training a model. First, we make a forward pass to the network and we provide a prediction. Second, it compares the prediction to the ground truth or loss function, which outputs an error value indicating the performance of the model. And lastly, it uses the error value to perform backpropagation, calculating the gradients for each of the nodes in the network. The gradient is a value used to optimize internal weights to facilitate network learning. Okay, now with that in mind, we encounter the vanishing gradient problem. The vanishing gradient problem describes the situation when neural networks are unable to propagate useful gradient information from the output end of the model back to the layers near the input end of the model. However, when performing backpropagation, each node calculates its gradient with respect to the gradient of the layer before. Therefore, if adjustments to the layer before is small, adjustments to the current layer will be even smaller. This causes gradients to shrink in size as it propagates down, where early layers fail to do any learning as internal weights are being barely adjusted. You can see this being represented by the diagram on the right-hand corner. Due to the vanishing gradient problem, our model does not learn long-term dependencies across time, which means that there exists a high possibility that information passed at the start of the text is not retained. This remains true for very large paragraphs and documents of text, especially. Okay, now this problem, there are other neural network models available, such as GRUs, LSTMs, and transformers. These models are very similar to the RNN architecture discussed already, but contain control gates that will direct the flow of information. These can be discussed with demonstrators later. But for the meantime, to summarize, we've gone through how textual data is processed and evaluated. We've learned how why feed-forward neural networks fail at sequential data, and how RNNs work and how they process sequential data. And finally, we've learned about the vanishing gradient problem and some possible other models that work with them, that work well at combating the vanishing gradient problem. All right, now for this section, let's head into breakout rooms for a little bit, and let's discuss these topics to, well, try to retain what we've learned. See you guys soon.
To a lot of dangers. The third point is immoral intent. So without controlling who gets to use certain AI technology, technology can be used for immoral deeds. An extreme case that you can imagine are robots designed to kill people, or the use of bots to interfere with social media and mine for personal information illegally. The fourth point is fake media. The rise of fake media created by these bots can overlap reality. For instance, AI bots can fabricate social media posts, create deep fakes and followers. People use this to their advantage to propagate their image on these platforms and gain sponsorship and deals. This, however, causes disadvantages to companies and individuals paying the people during the advertisement. The fifth and final point is AI biases. So we saw an example of the unfairness of AI last week, where in hiring and resume checking, more masculine language is favored in certain jobs. So human biases that are fed into AI systems can further marginalize already discriminated groups. So how do we use AI in an ethical manner? How do we maintain privacy while gaining insights from all of this collected information? So some of you have raised wonderful points before after the breakout session that we had, where you talked about AI and cultural differences in context of handling it and things like that. The honest answer to this is that it's an ongoing debate on how AI can be implemented, used ethically, and who is responsible for its downfalls. Although currently we cannot completely address all of these issues, we can implement a set of solid rules and regulations so that people with ill intent cannot take advantage of AI's capabilities and use or implement the technology in an unethical manner. Some sort of actions we can take as individuals or industries working with AI include identifying potential pitfalls, understanding human biases, enabling control over the AI systems, and ensuring that transparency and accountability is credited for. Defining who is in charge of artificial intelligence ethics has prompted much discussion. Despite an apparent agreement that AI should be ethical, there's a debate about both what constitutes ethical AI and which ethical requirements, technical standards, and best practices are needed for its realization. Some experts agree that legislation should lie the foundation for ethical use of AI, but in regulation, people argue that AI should be seen just like any other automated system. To tackle this issue to a certain extent, in Australia, the Australian Government Department of Industry, Science, Energy and Resources has its own set of 8 ethical principles. These principles are designed to keep AI safe, secure, and reliable. It aims to reduce the negative impacts due to AI and allow governments and businesses to be more ethical and responsible. So the first rule is that it focuses on human, societal, and environmental well-being, which implies that AI systems should benefit individuals, societies, and the environment. This means that there should be no implementation of killer bots made to destroy the world and no software is made to hack into other people's businesses. The second rule is that human-centered values, where AI systems should respect human rights, diversity, and autonomy of individuals. The third rule is fairness, where in order to prevent AI systems from being discriminative, it should be inclusive and accessible and should not involve or result in unfair discrimination against individuals, communities, or groups. The fourth rule is privacy, protection, and security. So AI systems should respect and uphold privacy rights and data protection and ensure the security of data. This means controlling who is able to access certain sensitive information. The fifth rule is reliability and safety. So AI systems should be reliable to operate in accordance with their intended purpose. And the sixth rule is transparency and explainability. So there should be transparency and responsible disclosure so people can understand when they are being significantly impacted by AI and can find out when an AI system is engaging with them. Transparency is gaining traction with companies such as Facebook and Google, which allows us to see how much of our data is being stored and letting us limit that too. So it is a key factor to make AI more trustworthy and reliable. The seventh rule is contestability. So when an AI system significantly impacts a person, community, or community group or environment, there should be a timely process to allow people to challenge the use of the outcomes of the AI system. This gives people the opportunity to come forward with any feedback. The eighth and final rule is accountability. So people responsible for the different phases of AI system life cycles should be identifiable and accountable for the outcomes of the AI systems. And human oversight of AI systems should be enabled. So therefore, people know who to contact and can put a name on the process of who designs what. So now that we've concluded with the FEM part of the section, let's move back to some NDN practical tasks.
Hey guys, so today we have 2 parts to a practical. We have a quick demo into reinforcement learning and kind of what we can do with reinforcement learning. And we also have some code to create a chatbot. So the chatbot part of today is going to use a data file called intents.json. I'm just going to go through quickly how we get that set up, just to hopefully prevent any errors. Because yeah, we need to set up our data to be in the right location, or else our code's not going to read anything and it's going to break. So now I'll quickly put in the links to the notebook and the data in the chat. Notebook, and here's the data. So when you click, so the first thing you're going to want to do is you're going to want to click on, actually, can I grab a screen share for this, actually? Okay, so when you click on the intents.json file, you should have the file come up. What you're going to want to do to set up the file is to come up to this icon to add shortcuts to drive. Click on that and make sure my drive is selected and then add shortcut. This should add a quick shortcut to your drive that should come up as like a kind of linked file. And now you should be able to run the code fine. Just a quick note, some of you might not have the icon there originally. The other option is, of course, you can download the file and manually put it in your drive. It just needs to be located in my drive and called intents.json. Other than that, in the workbook, we have a section on building a chatbot in which we go through, prepare our data, and build a model and train it. Then we can have a discussion with the chatbot. And then after that, we have a quick, we have a demonstration of reinforcement learning. So hope you all enjoy. Now I believe we'll be moving into breakout rooms to complete task.
One was an introduction to deep learning, as well as a snapshot of women in AI. Workshop 2 was about layers, model techniques, as well as going into data bias and improving minority representation. And of course, this workshop was about the applications of deep learning, as well as going through the data and ethics of working with AI. We really hope you guys have enjoyed this series of workshops. And especially if you have, I'd like you to fill out the feedback form that I've just popped in the chat. The link is also in the slides. But yeah, thank you so much for tuning into these workshops, and hope you've learned a little something